Hello everyone. I'm going to present a certain generalization of the notion of ultrafilters, and at the end of the talk, if time permits, then I will also cover ultra products in this setting. The talk consists of 3 parts, ideally. And let's start with the viewpoint that we can identify ultrafilters on a given set by a Boolean algebra homomorphism from the power set of that given set X to the 2-element Boolean algebra. And the correspondence is quite straightforward. If we are given such a Boolean algebra homomorphism, then the ultrafilter is the preimage of 1, or the true element. And the other way around, if we are given an ultrafilter, then we can send every ultra big element to 1 and every other element to 0. And that is what I want to stress here is that the Boolean algebras have finitary unions and intersection operations, and it mirrors the finitary intersection property of ultrafilters. Yeah. Here we can also identify the power set of X by the Cartesian product of the 2-element Boolean algebra 2 of itself X many times via the characteristic function. And we have this familiar notation that we denote by beta of X, the set of all ultrafilters of X. In the generalized settings, I will denote it by gamma. Not so precisely, but yeah. So the generalization is quite straightforward. That here, this category of Boolean algebras can be replaced by an arbitrary or almost arbitrary category, and the object 2 can be replaced by an arbitrary object therein. And that is going to be the generalization that I'm going to present here. And that's what is written here. So we are going to fix an object of an arbitrary category L, and so far the only condition on that arbitrary category L is that it should have products. And then in this setting, a generalized ultrafilter on a set X is going to be a morphism in this category L from L to the X to L, where again L to the X means the categorical product of L with itself X many times, which means that we have canonical projection arrows in the category of L that satisfies a universal property. So as I mentioned earlier, let gamma of X denote the set of these generalized ultrafilters, assuming that we fixed the L object and the L category. So it should be like gamma sub L prime curved L. And here I'm going to give only one example, but later implicitly we will meet actually all the examples. And this example is almost the same as in the beginning. So the object would be still the 2-element Boolean algebra, but the category is replaced by the category of kappa complete Boolean algebras. So Boolean algebras that have kappa-fold intersection and kappa-fold union operations. Not so surprisingly, in this setting, the gamma of X will give us the kappa-complete ultrafilters on the set X. So the ultrafilters that are closed under kappa-fold intersection, where kappa is any cardinal. We have similar properties of this gamma operation than the properties of beta of the ordinary ultrafilter operation. it behaves like an extension operator, meaning that we always get a canonical function, which is almost always an embedding, but there are some pathological cases where it is not, but this function always exists. We can map each element of the set X to the corresponding projection, which is this pi x is always of this form. It's always a morphism, this projection from L to the x to L. So it lives inside gamma x. These are the principal generalized ultrafilters, the pi x's. The second property is also about this extension operator. So whenever we are given a function to an extended set, so to a gamma of y for some y, then this function canonically extends on the domain from x to gamma x. And here you can read the proof, which actually only uses the product definition, where this function f is considered as an x tuple of elements of gamma y. So it's an x many arrows of this form from L to the y to L. And by the product definition, they induce a unique arrow, f hat, which in turn induces this extension, which also behaves well with this property 1. Okay. There's a familiar property of the ultrafilter construction, namely that it preserves the semigroups, in the sense that whenever we have a semigroup operation on a given set S, then it will induce a semigroup operation on the set of ultrafilters, and actually also in this setting on the set of the generalized ultrafilters. And actually, this third property actually is a consequence of the first two properties. Well, alongside with some more hypotheses. And also these first two properties are basically the statement that gamma, this correspondence gamma, is a monad on this category of sets. So this is our turning point to monads. And we can actually define monads by these two properties, basically, this one and two properties, and this is going to happen here. This definition was given by a characterization of monads by Kleisli. And it is so general that it applies to any category C, but here C will be always the category of sets. I think I don't want to go into details. So these are the properties that I didn't mention earlier, but these are also satisfied with for the generalized ultrafilters. So it means that for any fixed category L and an object L therein, the previously defined gamma is always a monad on the category of sets. And I just wanted to make a side note here, but maybe I don't want to do that, that these properties 1, 2, 3 correspond to the notion that the monads are monoids in some category of n functors of blah blah blah. The first property corresponds to eta being a right identity. The second property can be rewritten in this form, so it is more symmetrical, and this corresponds that eta is a left identity in the same sense. And the third property implies the associativity in that setting that I am not going to mention more deeply. So far all we know that this gamma operation is always a monad on the category of sets. And actually, the main theorem of this talk is that the converse is also true. So every monad on the category of sets is actually coming from this construction. We can construct a category L and an object L therein, such that the previously defined gamma, this set of the generalized ultrafilters, is naturally isomorphic to this given monad. And the proof relies on the fact that every set X is the coproduct of the one-element set with itself. We use here coproduct, so there will be a step when we use opposite categories in the proof, and also for a given monad, Claeysli defined a category for that monad, and that category construction is used also. This actually is a very simple theorem, especially after these hints. And now, if we can also turn to multi-valued logic. So what happened in the beginning that the two-element Boolean algebra was replaced by an arbitrary object, and based on this idea, we can continue, and so we can handle this arbitrary object L as the object of the truth values. I think I want to drink. So L will be regarded as the abstract object of the truth values. But to do this, we need actually more conditions on the category L, namely that it should have free objects. In the sense that there should be a functor U from this category L to the category of sets, and this should have a left adjoint, and this left adjoint will give us the free objects. Actually, this U should need not to be faithful or anything, so there's no more condition here. And then we can imitate the propositional calculus, the formulas over a given set X of propositional variables would be the elements of f of x, but this f of x lives in the category L. So what do I mean by elements of it? Of course, I mean that the elements of the U of that, so U of f of x. So we regard here the U, though it is an arbitrary functor, we regard it as the underlying set functor. And so what do we have in propositional calculus? That we have an arbitrary evaluation of the propositional variables. No, not in the two-element Boolean algebra, but in L. So every propositional variable has a truth value, then it naturally extends to the set of formulas. But what does it mean, this X to L? So X is a set, but L lives in the category L. So again, what it means is that this arrow actually lives in set, so it goes from x to u of L, and this extension is actually nothing else but the adjunction that we imposed at the beginning. So that's all for the propositional calculus. And we can also do some first order logic that I'm not going to give the details here. I only mentioned this generalized ultraproduct in this setting, but for this we define an n-ary L-valued relation just as an arrow from A to the N to L, where A is a set. And again, I didn't write it here, but it is meant as an arrow in set, so from A to the N to U of L. And we also need to assume an equality-like relation, probably as a part of the similarity type. And that should be part of the models, of the first order models in this setting. And in this case, actually, if we are given models A sub I for each I in the index set I, and if we are given an ultrafilter and this kind of generalized ultrafilter U on this index set, then we can define the ultraproduct of A of I's actually on the product set of A's, but we modify the equation or the equality. Namely, we modify it like this, which can be spelled out like this. And actually, this is all what I prepared for this talk.